So in the last chapter, we introduced stereoisomers for the first time, and that those are molecules that have the same bond connectivity. In other words, they are both 1,2 dimethyl cyclopentenes in this case shown here. But those methyl groups are in different spatial arrangements. And so here on the left-hand side, both of the substituents are on one side of the ring. And then on the right-hand side, one's on one side of the ring and one's on the other side of the ring. And you can't just bend the molecule around to get from one molecule to the other or get from one conformation to the other. These are actually isomers. They're different molecules. They have different properties. So we put a cis in front of the name for the one on the left, trans in front of the name for the one on the right, to distinguish between those two different molecules. So you can also have cis-trans stereoisomers for alkenes. And so you can see if you draw, let me find my pointer. There it is. So if you draw a line along the alkene, for the trans molecule, you have a methyl group on one side and a methyl group on the other. Kind of like with the ring, you had a methyl group on, or a substituent on one side and a substituent on the other. Whereas for the cis molecule, you draw that line again along the alkene, you'll see that both of the substituents of the alkene are on the same side of that line, like they were on the same side of the ring, and we call that cis. Do note that the rest of the name, but2-ene, is the same. The only thing that's different is that stereoisomer adjectives kind of in the front. So note that these two molecules are non-superposable. In other words, if you try to put one on top of the other, they don't align perfectly. One methyl group's going down, the other methyl group's up, and you can't do anything to these molecules to make them align. And the other thing to note is that they aren't mirror images of each other. And so we have a specific type of name for these types of stereoisomers called diastereomers. So we'll come back to that in just a few minutes. So as I kind of pointed out, you can tell if isomers are stereoisomers or constitutional isomers from their names, and that's usually the easiest way to do it. If any part of kind of the base of the name or the functional group or the substituents or the number in the front, if any of those are different with the names, then you have constitutional isomers. However, if the whole name is the same, except for that little adjective in the front, cis or trans, notice that the rest of the name is all the same, then you have stereoisomers. So that's going to continue to be the case. As I mentioned, when I mentioned diastereomers, we're going to come back to them, and we're going to look at them just for a second here, but then we're going to focus on enantiomers for the rest of this conversation, and we'll eventually wind back to the diastereomers next week, I think, or at least in a later little lecture here. So we've now seen a couple of different types of stereoisomers, and whether we're talking about enantiomers or diastereomers, the name of the molecule is going to be the same, except for that little bit in the front. All right, so to understand enantiomers, which is the direction that we're headed in right now, is that we first have to start with this idea of chirality. And chirality, or chiral, it's not chiral, it's chiral. These objects cannot be superposed on their mirror image. What that means is if you take your hand and you lay one on top of the other, your thumbs do not overlap. And so what that means is that your hands are not cannot be superposed on their mirror image. So your hands are mirror images, but all of the parts of them don't line up if you put one on top of the other. Okay. And so the reason that we get this thing called chirality has to do with symmetry. And so some objects are symmetric, they have a plane of symmetry, and other objects don't. And so things like A glass has a plane of symmetry down the middle. I didn't do a very good job with that. Soccer ball has a plane of symmetry down the middle. And what happens with this is if you take the mirror image, you can then superpose that on the original object. Whereas if you look at a pair of gloves or a golf club or these other objects, if you look at their mirror image, the mirror image cannot be superposed. And that comes out of that symmetry. So it's symmetry that determines that. So molecules can also have symmetry, and if they do have a plane of symmetry down like here, or this one's a little hard to see. I've got it already blocked off, but it's kind of between those two chlorines and along the bromine and hydrogen bonds, or the carbon bromine and carbon hydrogen bond, pardon me. This one does not have a plane of symmetry because the bromine's on the wrong side. If you reflected, well, it's actually on the one on over here. So, but if you reflected this, this is the mirror plane. If you had a reflection of it, then this bromine would also be going up. So this is not a plane of symmetry. I'm not sure if I can get rid of that, but I'll just put an X through it. There you go. Plane of symmetry, and then this one does not have a plane of symmetry. So if you do not have a line of symmetry or a plane of symmetry in your molecule, then you end up having a chiral molecule, just like with any object. If you don't have a plane of symmetry, then you wind up with a chiral object. But for molecules, organic molecules, the most common reason that you end up getting an asymmetric molecule is because you have an sp3 hybridized carbon with 4 different groups bonded to it. And hopefully that makes sense, right? If this ethyl group was a propyl group, like this group over here, then there would be a plane of symmetry down the middle. But since all 4 of these groups, the methyl group, the propyl group, the ethyl group, and the hydrogen, and let me just circle those. So methyl, this is the fancy chirality center. This is the thing we're looking at. There's 4 different groups bonded to it. Okay, that ethyl, the propyl, the methyl, and the hydrogen. Sometimes students say, "Oh, but there's carbons bonded," and so there's this. They're the same groups bonded. So there's three of the identical groups bonded to the chirality center, but that's not what we mean. What we mean is actually the whole group, the whole substituent bonded to this chirality center, not just a single atom. And so if you have 4 different ones, then your molecule has to be symmetric, right? Because each of these is different. There's no opportunity for symmetry there. So that's what you're looking for, and looking for chiral molecules, and chiral molecules are asymmetric, and you can tell they're asymmetric because they've got an sp3 hybridized carbon with 4 different groups bonded to it. It can't be sp2, it can't be sp, it's got to be sp3. So just take a second, you might want to pause this and see if you can label the chirality centers. Those are the carbons that have 4 different groups bonded to them, and they have to be sp3 hybridized. And now I'm going to click to the next slide and show you the answers. These are all biomolecules. So we have a dipeptide, that's 2 amino acids bonded together by a peptide bond. And we've got actually every alpha carbon, except for glycine, for your amino acids, does have a chiral center, chirality center. Carbohydrate, assuming this is glucose, but it has the 3 chirality centers, each of those bonded to an OH group. It's very water soluble. Let's see, I guess that would be an RNA nucleotide or nucleoside, and it's got the 3 chiral centers down here. Maybe I've missed some. And then we have a lipid, a triacylglycerol, and we have our sp3 hybridized carbon with 4 different groups bonded right here in the middle. All right, so that leads us back around to enantiomers. And so remember that Types of isomers, broadly, isomers are compounds with the same molecular formula but different structures. We've looked at constitutional isomers. We've looked a little bit at diastereomers, but we need to wrap back around to that later on. And so now let's just define enantiomers. They're mirror images of stereoisomers that cannot be superposed. And so let's just look at what those words mean. That I have superimposed crossed out on this. Those two words are commonly used interchangeably, but they actually mean different things, superimposed and superposed. So superimposable means that you just kind of lay two objects on top of each other. But superposable means that when you do superimpose them, when you do lay them on top of each other, each atom coincides exactly. So we're really talking about superposability here. So molecules that are mirror images and not superposable are called enantiomers. And every molecule that has one chiral center or more than one chiral center will have exactly one enantiomer. An enantiomer is simply a mirror image of your chiral molecule or chiral object. And so any mirror image, you only get one mirror image, so you can only have one enantiomer. And so these are the mirror images down here. This is actually a really common way of drawing mirror images. Imagine there's a mirror right here. And so if this was the reflection of this molecule here, then the backbone would go the opposite way. And on the third carbon here, you have your hydrogen that's still coming toward you and that methyl group that's still going away. So these are non-superposable, meaning that if you tried to align all of the atoms, you wouldn't be able to do so. These are actually isomers. They're two different molecules. They have different properties. Okay, so let's look at a simpler example of what it looks like to superpose or not superpose. If we look at an achiral, oh, it's missing an O, an achiral carbon or an achiral molecule, if here's the mirror image on the right, and we simply have to turn the molecule on the left around, kind of just rotate it. I guess it says that up here. I don't need to draw it there again. You rotate it, and you can see that if you superimpose the molecule on the left with the one on the right, you can see that they're the same molecule. The bromines line up, the hydrogens will line up, the chlorine will line up. But if you have one of those molecules that's chiral, then the enantiomer, the non-superposable mirror image, will not. You can't line these molecules up, and so you can't superpose them. So here is our starting molecule. Here's the mirror image, the enantiomer, and so no matter how I try to rotate the one on the left, I'm not going to be able to make all of the atoms line up with each other. And so that's what we mean by superposability, or that these can't be superposed.